we're going to go ahead and get started with homework 3 for controls part A. What we're doing here is we're taking a single gravity drained tank and we want to derive the transfer function for that. So I'm going to walk through kind of how I can do that by taking a Laplace transform, and so I'll just get right into it. Alright, so like I was saying, we're going to derive the transfer function, but for a single gravity drained tank. We're going to linearize the equation that relates the liquid level to the inlet and outlet flows. We will subtract the steady state solution and take a Laplace transform of the deviation variables. After that, we will find the gain and time constant for the resulting first order transfer function. From our previous videos, we know that the derivative of the density times the area times the height over change in time is equal to the density times the flow rate in minus the flow rate out. And then we see that these densities can cancel, and we can simplify this a little bit further. We know that the area isn't going to change, but the height of the liquid will change. So we can pull that A out, and then we have Q in and Q out still. Something else that we derived in a previous video is this flow rate. We can represent it as the height times 2gh, and we're actually going to create a constant, and so that we can simplify our writing a little further. This is going to be the area out, so the area of the whole of the tank at the bottom, times the square root of 2g, so that we can rewrite this equation. Then we can write it as A dH dt is equal to Q in minus this alpha times the height to the 1/2 power, just taking it from here. And in order to take the Laplace transform of this, we need to linearize as stated above. We're going to linearize the equation. So I'll just underline that there. And to linearize this, our only issue is this 1/2 power. And so if we want to get rid of that, we can approximate this as something else. We're going to say this is approximately equal to this h bar. H bar is the steady state height, or steady state liquid height specifically. Need to add 1 over 2 square root of h. This is evaluated at h is equal to h bar, and then we multiply by the difference of h minus h bar. And then, like I said, this h bar is the steady state liquid height. And now we can also approximate this equation. We made it so that it could be linear. So combining these two, we can say that A times dH dt, the change in liquid height over time, is approximately equal to Q in minus alpha times h to the 1/2. We said h to the 1/2 was this whole term, so we're going to multiply by exactly that. We can also write the steady state equation for this. We know that dH dt would be 0 for a steady state, and then from all the way above we have Q in minus the alpha times h to the 1/2, except this is the steady state solution, so we're going to add those bars to the top. Again, because it is specifically steady state, we want to make sure that we don't confuse those with the actual values. Now we want to subtract these two equations. I'll do that right here. So we would have a dh over dt minus 0 is equal to qn minus alpha times h. I'm going to start writing that as h to the 1/2. And then we're subtracting the second equation, so that makes this piece right here positive. And I forgot to add a 1/2 power here, but there should be a 1/2 power on those h bars. So hopefully I caught all of those. And now we can see that we have some term cancellations. We have a negative alpha h bar to the 1/2 and a positive alpha h bar to the 1/2. And we get our equation from subtracting those two equations. In the more simplified form, we can say it's qn minus the flow rate in at steady state. So this is not steady state, and then we're subtracting the steady state solution. And then we'll go ahead and subtract our alpha times 1 over h bar to the 1/2, because we're evaluating it at h is equal to h bar. And this is also multiplied by h minus h bar. So now we've gotten to this point, we've subtracted the steady state solution, and now we want to go ahead and take the Laplace transform of the deviation variables. The deviation variables we will define as follows. We're going to say that the deviation variable for the liquid level height, we're going to denote it with this little apostrophe, is equal to the difference in the height minus the steady state height, which you can see up here. And we can say the same thing with the flow rate, and that was up here. Then we can rewrite in terms of those deviation variables. Just to make it cleaner for now, that's what we're doing it for. 1 over 2 h to the 1/2. And then we're multiplying that by the height deviation variable. And actually this dh dt is now in terms of the deviation variable, just to point that out. And now we can isolate the differential and write it out like this. Something I do want to touch on, instead of just glossing over it, is why these two differentials are equal to each other even after your this one's the deviation variable, so that would be the h minus h bar that we defined up here. That is because dh prime dt is equal to dh dt minus dh bar dt, and as we discussed, this is steady state, so it's 0. And that's why these two are equal to each other. Now we have our equation. I'm just going to copy that down here. And what we want to do now is take a Laplace transform of our equation. Right here, I just wrote out a general form that our Laplace transform takes, specifically for a derivative, so that should be a prime. So we're taking the derivative of this. Deviation variable differential. And so that would be SH. So this H is the Laplace transform of our height. So we're just switching that over to the convention of making that a capital letter. We also need to subtract F0, but again, the reason for doing some of this was that this is steady state and it's 0. Similarly, taking this Q in, taking the Laplace transform of that, we just get a big Q in. And that means that we now have enough information to rewrite this. The equation that I have circled above. The area does not change in this, so we still have the 1 over A. Now we have the big Qn subtracting the alpha over 2 h bar to the 1/2 times h. That should be big H. And then we want to get this in terms of, well, we want to get h by itself. So we have that term with the alpha, and again, just to remind you and myself that the alpha is the area of the whole times the square root of 2g, g being the gravitational constant. And I should also have an area down there. And then that is equal to Qn over the area. Then we get our equation in terms of just the height. So we have Qn in the numerator, and then in the denominator we have all of this stuff. So in general, this equation right here describes our system. So that describes how basically the liquid height level changes with the flow rate in, also depending on the area and those things. But what we want to do also is to find the gain and time constant for our transfer function. In general, this will kind of look something like a k over tau s plus 1. Up here is our gain, and then this tau is our time constant. So we want to get our equation up here into this form. So we need to do something with that Q in for sure. we need to substitute those values that we defined previously. 2a h to the 1/2 divided by the alpha that I defined. And this is skipping a few steps, but essentially we needed to get rid of this term, so you have to multiply by the inverse, and this is what we are left with. And again, this should be h bar. And then we are left with something that looks like this. And after one final cancellation of these areas, we get that the height is equal to 2h bar to the 1/2 over alpha divided by 2a h bar to the 1/2 divided by 2ah bar to the 1/2 over alpha times s plus 1. And now we're in that form that looks like this, because we got rid of this term. And now we can say that this is our gain, and this is our time constant. More explicitly, the gain is 2h bar to the 1/2. Again, h bar is the steady state, divided by alpha, alpha being the area of the hole times the square root of 2g, and then the time constant. Looks very similar, but includes the area. And so there we go. We started off by linearizing the dynamic equation, and then we kind of looked at the steady state of this example and subtracted the linearized equation that we had from the steady state solution. We also introduced these deviation variables right here, which helped us to get to our nearly final equation that we needed to take the Laplace transform of. So we did that, and we got our transfer function. Our transfer function right there, our gain here, and our time constant. And I'm just now realizing I never really drew out a diagram, just because this, it's kind of simple, I suppose. But we have our tank. Going in is our flow rate. Coming out is the height we observe. But in the Laplace domain, it looks something like this. And then this equation that we calculated up here, see if I can copy that. So that equation that we have from up there describes how this system behaves, essentially. In the next video, we are going to move on to 3 identical gravity drained tanks rather than just a single tank. So this was more of an introduction to kind of how to get around that, and hopefully we can just hit the ground running in the second part of this homework. And I'm going to skip my end screen, but thank you for watching, and I hope that you stay tuned for the next video.